So I'm going to be talking to you guys about formulas specifically for computing finite type non-invariants. If you were here for the last talk, you're like primed and ready to go, which is really awesome. But before I talk about knots, I wanted to introduce myself because this is the Math for All conference. I'm a visiting assistant professor at Boston College. I do research in computational and algebraic topology. Of all the classes that I've taught or TA'd, my favorite so far is linear algebra, but my dream class that I hope one day I'll be able to teach is topology, fingers crossed. And then I guess for those of you who are just starting off in your journey of being a mathematician, I wanted to talk about like my favorite part of being a mathematician, aside from the actual math. Groups like Women in Topology, that's a AW advanced group that I've like met a bunch of collaborators through. I really like being a part of that group. And then conferences like UStars and Math for All, where I feel comfortable and happy to talk about my math research with people. Okay, so I am gonna kind of go a little bit quicker through the beginning of my talk than I would have for those of you who already have seen this, but maybe for you guys who weren't in this room. So I'm going to be talking about computing finite type non-invariants. First of all, what is a mathematical knot? Well, if you guys like picture what you think a knot is in your head, you might see something like this. And if you were here for the last talk, yeah, this is basically a knot as we think about it as mathematicians. The only thing we might change is taking these two endpoints and kind of gluing them together. Okay. So when you're thinking about when I'm talking about definitions, you guys can kind of like just keep the picture of like a rope being tied up in your head, and you're gonna pretty much be on the right track. I found this quote in a book, Introduction to Knot Theory. I just really like it because it's kind of like low-key, like kind of aggressive, but like also very true. Math never proves anything about anything except math, and a piece of rope is a physical object, not a mathematical one, right? So we can have this picture of a knot in our head, but we need a actual mathematical definition of a knot, which is just a closed curve. I think about it in R3. If you think about an S3, don't worry, like we're pretty much thinking the same thing, right? What does that mean for it to be a closed curve? Well, I think about knots as maps from the circle into Euclidean space, which always have a non-zero derivative and which are always injective. So these are just nice smooth embeddings of the circle into three-dimensional space, okay? And I'll talk about two different ways to kind of visualize what a knot is. So the first way that I kind of like visualize knots is through what are called plane diagrams. So to make a plane diagram for a knot, what you do is you take your embedding in R3 and you just project it to your favorite plane. Okay, so take this physical yarn ball that you've kind of created, drop it on a table, and draw what you see kind of on the table. Okay. So when we do this, when we project something three-dimensional into two-dimensional space, right? We have an embedding in R3. That means we don't have any points which intersect. But in our plane diagram, we might have places where more than one point project to the same point in the plane. Okay, so if this happens, when two or more points in R3 project to the same point in the plane, we have something called a crossing. And you can see that we're gonna like visually depict this in our plane diagram by drawing one of the strands on top and one on the bottom, just kind of remind us like, hey, that's not actually like a self-intersection point in R3, like we have an embedding, okay? And we call a plane diagram regular if no more than 2 points project to the same point in the plane. So we have kind of like these single crossings, 3 strands don't kind of overlap in one spot. So here's the unknot. Here's a trefoil. You can see I'm using oriented knots here. So if we give the circle that we're embedding some orientation, say counterclockwise, our knot's going to have an induced orientation as well. So I like to also think about oriented knots, just like Madison and Sarah. We're very similar in lots of ways. Okay, cool. And so the last thing to kind of know, these regular plane diagrams where I only have 2 points projecting to the same point in the plane, these types of projections are dense in the set of like all possible projections of a knot, right? So if I saw, if I took my knot, I dropped it on the table and somehow 3 strands did cross over, I could like flick one of the strands a little bit and I would get a regular plane diagram. So like most of the plane diagrams are going to be regular plane diagrams. Okay. Okay, cool. So a big goal in knot theory is to try to differentiate knots, right? When are two knots the same? When are two knots different? And there are lots of measures of this. The way that I think about two knots being the same is through isotopy. So I'll consider two knots to be isotopic or equivalent if they can be continuously deformed from one to the other in R3 without ripping the thread or self-intersecting or tearing. Okay, so kind of like knot concordance, a little bit stronger. Okay, and in practice, again, like Sarah Madison said, finding out if two knots are equivalent, this is not an obvious goal, especially kind of if we think about knots as plane diagrams, which I showed you before. You can't just like look at like two knots and be like, oh, those two knots are the same. Like that's really hard to tell. And just to like convince you of this, take a minute to look at these. And by a minute, I mean like maybe 5 seconds, right? If someone showed these three knots to you, like, would you say these are equivalent or not, right? You kind of can't tell, right? With this one here, if I am very tricky and I look at this, I can kind of see that maybe I can take, like if this was a three-dimensional object, I could take this piece, flip it over, I would get the unknot back, right? So I could maybe know that this knot here is equivalent to the unknot. These two knots here though, like that's really hard to tell. There's a bunch of crossings. I don't really know what's going on. And actually both of these knots are equivalent to the unknot. You just basically have to know how to isotope them to the unknot. Okay. So we can't tell just by looking. So how are we going to tell if two knots are equivalent through isotopy or not? Well, that's where knot invariants come in. Okay. So a function, ooh, I don't need that up here. A function is a knot invariant if it takes as its input a knot, and for any two isotopic knots, it gives the same value. Okay. So that's any function that does this is as a knot invariant. Okay, so for example, I can define the following knot invariant. Okay, I take a knot K, right? I give you a 1 if K is isotopic to the unknot, and I give you a 0 otherwise. That's a function, takes as its input a knot, and it's going to give you the same value for any two isotopic knots. This is not like a super helpful knot invariant. If I actually care about taking like two real knots and seeing if they're isotopic, it doesn't really tell me how I'm supposed to determine if this knot I'm given is isotopic to the unknot or not, right? So it doesn't really give me instructions. And it's also kind of not helpful in that like this tells me whether a knot is the unknot, but it doesn't tell me if two knots which are not the unknot, if they are isotopic. That was a mouthful. So the converse might not be true, right? So for knot invariants, we might have two knots which are not isotopic giving the same value. And in this case, right, we would say that this knot invariant does not separate those two knots, okay? A knot invariant does separate two non-isotopic knots if it spits out different values for those knots, okay? So this is kind of a goal of knot theory, to find a knot invariant which separates all knots, right? So a knot invariant that actually would spit out different values for knots which are not isotopic. And that just hasn't been done. It's very hard. So we're like, okay, let's like step back a little bit. Maybe I can find like a group of functions, a group of knot invariants which separates knots, okay? That still is an open question. We think we have some types of groups of knot invariants which might separate knots, but we're still not 100% sure. And so what I research and like what I think about are what are called finite type knot invariants, which have several really awesome, cool, interesting ways in which they are derived that I'm not going to go into. But the takeaway and what you should think of finite type knot invariants are as is a group of knot invariants, which is thought to separate knots. Like it pretty much probably does. Like we think so, fingers crossed. And these are also not invariants, which are actually computable. So these are not invariants that like I actually know how to compute. They show up all over the place, but that's kind of like the cool thing is like I can tell you how to exactly compute a finite type knot invariant from a plane diagram of a knot, and it's through something called the Gusarov theorem. Okay, so to kind of tell you how you might compute a finite type knot invariant, first, I need to tell you about a second way that you can visually depict a knot, okay? And this is through something called a Gauss diagram. So a Gauss diagram is an oriented circle with a distinguished set of distinct points divided into ordered pairs. So I've got three adjectives here: distinguished set, distinct points, ordered pairs, and each pair carries a plus or minus sign. Okay, I'm going to show you how to make a Gauss diagram. You'll understand a lot better what it is once I do that. But every regular plane diagram of a knot can be associated to a Gauss diagram, and I'm going to use these Gauss diagrams to compute finite type invariant values for knots. Okay, so how do we get this Gauss diagram? Okay, so I take a plane diagram. Okay. In order to generate a Gauss diagram, first thing that I need to do is I need to label the crossings of my plane diagram as either plus or minus. Again, just like in Sarah and Madison's talk, when we have orientation, we can give a sign to our crossings. So plus looks like this, minus looks like this. With this plane diagram of the trefoil, if you go through, like we can draw arrows here to maybe kind of like zoom in and see what types of crossings we have. So if you like zoom in a little bit there, you'll actually notice that all of these are positive crossings. So we're going to give every single crossing a plus sign. Okay. And the second thing I want to do is I want to number my crossings starting from like some base point. So I'm going to give my knot a base point, means start here. I follow along my knot, following the orientation of my knot. And I'm going to number the crossings in the order that I encounter them following along the orientation of the knot. Okay, so this gets 1 because I pass through this crossing first. This gets 2 because I pass through this crossing second. And then this gets 3 because I pass through this crossing last, following along the orientation. Okay, cool. So I have my plane diagram nicely labeled. Now I need to create my Gauss diagram. Okay, well, my Gauss diagram is a oriented circle. Let's put an oriented circle over here. Okay, I'm going to put points, pairs of points on this oriented circle. And for each crossing, I want one pair of points. So you can see I already have labeled here like 6 points. And that's because I have 3 crossings. Each crossing is going to get 2 points. Okay. So I'm going to number these points, again, starting at like some base point. So let's put a base point here. I'm going to follow the orientation of my circle, and I'm going to label my points with either a 1, 2, or 3. Again, kind of being like, okay, when I start at my base point, I hit my first crossing first, right? So this first point is going to get a 1, kind of saying like, okay, you pass under the first crossing there, right? This second point is going to be 2. This third point is going to be a 3. Right? But then, when I labeled my crossings, I didn't keep going to end up all the way back at my base point. So I'm going to pass through each of these crossings again, right? I pass through each crossing twice. If I start at one point, I end up all the way back where I started. So after I hit this third crossing, I go through the first crossing again, and then I go through the second crossing again, and then I go through the third crossing again. Okay, so each crossing has 2 points. I'm going to connect those points with a chord. Okay, so these are my pairs of points, right? And I want ordered pairs. The way that I'm going to depict this order is by making each of these chords an arrow, where my arrow points to the place in the knot where I pass through my crossing on the overstrand. Okay, so for example, right, the first time I pass through the first crossing, I pass on the understrand. And then the second time I pass on the overstrand. So my chord is going to be an arrow which points to the second time that I have the point 1 on this Gauss diagram. Okay. this chord for 2 is going to be oriented this way because the first time I pass through the second crossing, I pass around an overstrand. I've got an arrow here. And then finally, my chords get the same sign as the crossing. So I get plus, plus, plus. Okay. Give me a thumbs up if you like know how to make a Gauss diagram now. Okay, great. Everyone does. Okay, great. That's wonderful here. Okay, cool. So I love Gauss diagrams, right? They're really awesome. Each crossing here is represented by one ordered pair of distinct points. And then kind of lastly, right, so like this is like maybe even more abstract of a way of visualizing a knot than like the plane diagram. At least with the plane diagram, we kind of like maybe could see what it is. So just to like go back, right, each of these arrows represents a crossing, right? Each of these crossings is actually like in R3. If I think about it, what this arrow is representing is it's representing 2 points on like my embedded knot in R3, which are, if I took the difference of the 2 points on the knot, I would get a vector which points straight up. So there's kind of like a hidden geometry in this, basically. These arrows are saying, if I think back in like my actual embedding in R3, I'm finding points which are like collinear. And not only are they collinear, like the vector, the line between these two things is like straight up. Okay, cool. Awesome. This is great. I'm going way faster than I thought I was going to. This is awesome. Okay, so we got our Gauss diagrams. Within any Gauss diagram, you could think about a sub-diagram, right? So if I just picked up these two arrows in my oriented circle, that would be a sub-diagram of the Gauss diagram of this knot. And what I actually want to do to compute these finite type knot invariants from Gauss diagrams is I want to count specific sub-diagrams that I see within the Gauss diagram of a knot. Okay, so here's some notation. Just think of like some random Gauss diagram, just some oriented circle with arrows, right? We define the following notation with cool Langle, okay? GI comma GK just tells me the number of times that a specific Gauss diagram appears as a subdiagram in the Gauss diagram of a knot, right? So I can take any Gauss diagram I want, and this product here is just going to be the number of times that specific Gauss diagram shows up in the Gauss diagram of a knot. Okay, so like drum roll, this is actually how you compute finite type knot invariants from knots. Okay, you're going to count subdiagrams, and here is your first example of a finite type knot invariant. It's called the Casson invariant. Okay, it's the simplest finite type knot invariant, and I can tell you exactly how you can compute it. Okay, if you want to compute the value of this Casson invariant, you take a Gauss diagram of a knot, right? We have the Gauss diagram of a trefoil, and you count the number of times you see these two subdiagrams. They're basically the same, except for I've got negatives instead of positives. And I'm going to subtract away the number of times that I see like 1 plus, 1 minus with the same diagram. So what we're doing is we're counting signed embeddings of this unsigned Gauss diagram within the Gauss diagram of a knot. Okay. Cool. Yes. Awesome, Patty. You should do that. Okay, cool. So I can compute the Casson invariant for the trefoil, right? I just have to like look at my trefoil, right? And I'm like, okay, I'm looking for a pair of arrows where the base of the arrows, this is kind of like right next to the base point, and then the two heads of the arrows are here, and they have positive sign, whatever, right? I can compute the Casson invariant for the trefoil. It's 1. Cool. Okay, cool. So just to recap, and this is good, I think I have literally 1 minute and we hit my goal. This is the slide that I actually wanted to get to. There are formulas like this for any finite type knot invariant, and there are finite type knot, infinitely many finite type knot invariants. Any finite type knot invariant has some formula in which you count specific instances of specific subdiagrams within the Gauss diagram of a knot. And in fact, in the proof of this theorem, it's kind of like an algorithmic method of developing, like figuring out what these subdiagrams are. So not only do I know there exist these diagrams, like I actually really know how to find these diagrams, and they kind of make a lot of sense. So for any finite type invariant, someone can generate a Gauss diagram formula. And I'm just going to talk for like 20 more seconds because I actually want to say what, so this is everything up to my research. This method works if you have a regular plane diagram to start off with, but what if we want to compute a finite type invariant from a plane diagram which is not regular? Well, the issue we run into here is if I have a plane diagram which is not regular, if you remember when we were creating these Gauss diagrams, right, I had this distinct set of distinguished points which formed ordered pairs. I don't know how to do that if I don't have a regular plane diagram. So my research is looking to extend this method of computing finite type knot invariants to Gauss diagrams of projections of knots which are not regular. And it's really awesome. Okay, I'm going to be done because I don't want to like talk too much.